Water flood, right? I think most of the oil in the world is being produced with water flood. And what could actually go wrong with the water flood? You produce oil, you inject water, you support the pressure, the water displaces your oil, you get more oil. It's quite simple, right? But, you know, while having had experience with many subsurface teams on surveillance of waterflood projects, I can tell you that literally anything can go wrong with waterflood. And let's just run through several cases, and I will show you how it looks in the reality. Maybe some of you could get some flashbacks from your previous or ongoing projects. All right, so this is one of the fields which a while ago I had been surveilling. So this is how the water flood looked at start. So this is like the first year when we launched injection. You can see that everything looks pretty fine. We have a lot of oil producers, mostly zero water cut. We have a large amount of injection, so probably the displacement coefficient is quite nice, so everything looks fine. Let's see what happens in 5 years. Well, 5 years later, it doesn't seem so pretty. You can see that we lost, well, I think a half of producing wells due to watering out. So most of these wells have a lot of water now. Some of them are already shut. We also closed some injectors because it was clear that some injection wells were just putting water in producing wells directly. So it was like a giant laundry when the water went round and round in circles. So let's wait another 5 years and see what happens. Right. So it's been only 10 years of the field's history, and we have reached the rate of possible production of, like, I believe it was below 10. It was about 8%. So at this moment, the field is practically almost dead, and we only have taken 8% of the reserves we can actually get. So this is a sad story. It's quite old, actually. And now we have some technologies, we have some knowledge and experience on how to prevent this type of mistakes we made with this field, right? Okay, so before I go to the next, to the first case I want to show you today, I need to introduce you this technology, MRT, multi-well retrospective testing. So this is one of technologies that we are using to analyze the water flood. Not only water flood. I think some of you who joined me a couple of months ago in my first webinar in the beginning of April, which was on compartmentalization and static model adjustment with dynamic data, you might remember the description of the technologies, but still I want to say a couple of words. I think we have new people today. So this technology is called multi-well retrospective testing. The idea of the technology is that you have a long enough history of bottom hole pressure and rate in your wells. So it means that you need to have a PDG or ESP with a pressure gauge, and you store all your pressure data on some kind of server, and you have like several months or even years of pressure history in your wells. So if you have this data, then you might be able to see that when you change the rate of a well, a producer or an injector, then the offset wells, the wells around this well, will start changing the rate or pressure or both. So it means that throughout the history of the field development, we can see wells talking to each other. But we need to have this pressure data. So this is crucial for this technology, right? Here's how we do it. We have this well in the middle, which has a PDG, and we have several offset wells, some of them producers, some of them injectors. We call these several wells an MRT cell, and inside this cell we build a small mathematical model of these wells talking to each other, like a small interference model. That's how I would put it. So based on these small models, we may understand the reservoir pressure, the productivity index, and the actual history of cross-well pressure impact. So we can see which well is given the pressure to my well, and which well is taking the pressure, and how much pressure, right? All right, now let's jump into the case. The first case, well, I would call it a classic MRT case. So below here you can see the paper where you can see more details on this case. And it is a field-wide MRT analysis. So it means that we have a field with several deposits. You can see one of them on your screen. And this field is struggling with several problems. One of them is the fast increase of water cut in producing wells, and simultaneously reservoir pressure drop and non-uniform pressure drop. So we have high pressure somewhere and quite low pressure somewhere. Nevertheless, we have, well, a system, a pressure maintenance system, which looks quite balanced. So if we build a PIR plot and we build a map where we see the displacement coefficients, it would seem quite normal, but still we have some problems. Now, what are the problems? You can see that most of the producers are horizontal, and most of the injectors are vertical wells. So it means that in order to keep the displacement ratio, you need to inject a lot of water at a very high repression in the injectors. So it means that the drawdown, right, if I may call it so in injectors, the drawdown is a lot higher in injection well than in producers. And unfortunately, it is a Western Siberia case, I believe. So unfortunately, the permeability is, well, quite low, I would say. And due to this high injection pressure, we are getting induced fractures. And a lot of water, which we're trying to inject in the target layer, is in fact going into the underlaying pay, which is water saturated, because the shale break between them is quite thin. So this is a major problem. We know it's happening, but we don't know where, and we don't know what are the amount of this effect, right? So now we will try to estimate it with MRT. We are taking all the wells, all the producing wells. All of them have a very nice history of bottom hole pressure and rates, because the field is quite fresh, I would say. The active development had started in 2013, and then we interpret this data with the MRT workflow, and we focus on the injection impact. So it means that we're trying to understand which injector is bad, which is good, and in what way. So after we're done, we categorize these injectors into three categories. So category number one are injectors which are painted green here. So these are normal injectors, and by saying normal, I mean that the impact, the pressure impact of these injectors onto the offset producers corresponds with the transmissibility we have for this formation. So it means that it seems like these injectors are injecting most of water into the right pay, and we see the impact on offset producers. So around in these areas, it's pretty much all right. The second category are the injectors I painted in orange. So the orange injectors are the ones which are losing most of the water in the thief layer. So we see that the impact of these injectors is considerably weaker than it should be predicted with the transmissibility we have for this formation, the distribution of transmissibility, right? So by the way, it explains why we have these red zones here, because these red zones are the largest reservoir pressure drop zones. So during our MRT, for every producing well, we estimated the current formation pressure, and here we saw the biggest drop. And now we can see why, because these wells, several injectors with a very high rate, which were supposed to support these areas, are actually losing most of the water, like in vain. Okay. And the third category of injectors, we have only one well in this category here, the red one. Ironically, this is the well which has the least injection, but this is the only injector which has the direct breakthrough into the offset well. So we can see with pressure data that this well is actually flooding this X12 horizontal, and all this water we have here is coming from this small X05 well. So yeah, sometimes we can see scenes like this. And now that we know the picture, now that we draw all these color circles and these arrows, we may understand what to do. So we're trying to suggest something. So based on this analysis, we had a full scope of the recommendations, but I want to focus on one here, which is like the most straightforward, but still not obvious when you don't see the MRT results. So just outside this horizontal, you see another producing well here. It is vertical, and it is situated right inside the area of the pressure drop, and it's next to another injector, but now we know that this injector is insufficient, and we recommend to switch this producer into injection. All right. So after some talking and convincing, our client switched this producer into injection, and here is what we saw. So you can see the history of X12 well here, and this orange line is the moment when we started injection in X28. So you can see here that right from the start we had a BHP increase and liquid production increase, and in about a month we increased the pressure drop. The water cut dropped substantially, and we had like let me see, it's about 200 or 300 barrels of oil back into production on this X12 only. So it means that this X12 is really watered out by this injector, which in fact was closed before this operation, right? And it also means that there is a pressure drop in this area, and there is a lot of oil to the north from this horizontal, which it can perfectly produce, which if we just increase the pressure here, which we proved by these results. All right, another thing we can do is to justify the well's candidate for these treatments, well, let's call it EOR treatments. It's maybe not strictly correct, but in Russian oil industry we practice a lot this type of stimulations when in injecting wells with the supposed fractures we inject a viscous fluid, a small amount. Well, by saying small amount, I mean small amount comparing to the pore volume, but it would still be, well, several hundred cubic meters. And this fluid is supposed to block the fractures and prevent water from coming straight to the producing wells. I don't know if you practice some of those. By the way, guys, we have an open chat, and if you have some questions along the way, you please type away, and at the end of the presentation I will look through your questions and try to answer them all, okay? Right, so with this MRT we were able to see on this deposit or several other deposits, we were able to see several wells which have too fast pressure impact onto nearby producers, and we are supposing that these wells are causing the high water cut in those wells. So when we select this candidates for this treatment, we take into account the MRT results, and then in several wells we perform these treatments, and you can see that right, well, number 1, 2, 3, and you can see these red lines, which are the time of the stimulation on the injector, and you can see the water cuts drop and some oil production increase. Well, it's not much. I think it's well, around 100 barrels. But still, considering the low price of the treatment, this is a very nice result. Okay, let's go to another case. Another quite interesting case with MRT technology. We are trying to adjust target rates with MRT. So we have a completely different field. This is a very permeable sand, poorly consolidated with several Darcy permeability, but the problems are, well, I would say quite common. So we have a non-uniform reservoir pressure drop. We have areas with high pressure, with low pressure. We don't understand if there is any impact from the injecting wells. From some wells we do see the impact, but we cannot quantify it, and we would really much like to. Also, we have the anisotropy of cross-well interference. So we got the, inside this large pay, widely distributed, we actually have some channels which with even higher permeability, and we would like to see if through the cross-well impact it is possible to understand where the channels are, right? Also, we have the overall oil production decrease here, and well, we need to help our client with all these issues. So let's see what we can do here. So these are actually the results, and you can see some plots here. So we have a reconstruction of formation pressure history for the wells which were the focus well of our MRT cells. So we can see the blue line is the BHP, and the red line above is the formation pressure. And it's not just a line that we drew, it is actually a modeled line, and each curve on this line is an impact from the some offset producer or injector, right? So we now understand the how the wells are talking to each other, and producing and injection wells. Also, we reconstructed the productivity index history, because now when we have the history of formation pressure, we also have BHP, we have rates, so it's like a straightforward calculation to understand what the PI is like. And we can see that the productivity index has dropped in, well, at least one of the wells, and the drop is substantial, it's 20–30%, because considering the productivity of these wells, well, these drop of PI actually means that we are losing like hundreds of barrels of oil per day. We can understand why, because we have a skin raise, and the raise of skin is substantial, and we can see that the most probable reason for that is that the gas liberating is causing the dual phase zone near the well bore, and it decreases the productivity of the wells. So this happens because our reservoir pressure went below the bubble point during the time that we observe with our MRT analysis. Right, so also we assess the well and reservoir properties. You can see that the permeability, yes, it's quite high. It's around 2 Darcy here. We have a very high skin at the moment. And also we estimated the drainage volume of the wells. Right, so these are the raw results. And as to the cross-well impact, no, not yet. The next step is to predict the formation pressure. So we just take our interference model, and then we perform a forecast in a no further activity scenario. So we're trying to understand how the reservoir pressure would drop further. And we can see here that given the concentrates of the wells and the offset wells, we can see that in both wells we analyzed here, we have a reservoir pressure drop, and we predict a further drop. And in one well, it's pretty moderate, but in this well it's pretty sharp. So we can see that in no time we will have another major drop of like 15 bars, which is critical for this field, as this yellow line here is the bubble point. I think you understand what I'm talking about. All right, so I'm just trying to say that MRT results in this case are highlighting the necessity and the urgency to increase injection. We need to increase the formation pressure because we are already losing the productivity of our producing wells due to the fact that formation pressure went below the bubble point. All right. And the next thing is the cross-well interference. So we have these maps of interference and these values of cumulative monthly impact or daily impact. So what we can see here is that the well interference tends to be higher in the north-south direction. So it means that the probable structure of these channels is north to south. Another thing we can see is that around one of the tested wells we had one injector which is actually outside the barrier, and there was an idea that probably there is still a communication through the fault, but we weren't able to see any impact from this injector during the time that we tested this producer. So it doesn't seem like at the moment this injector is giving any pressure to this producing well. Some wells are closely connected, so it means that amongst other wells we have some pairs of the wells which are connected very tightly, and we can see that they are still in production from each other. For example, this well 365 and this well 255. So it's pretty far, but still I think due to this heterogeneity we have very fast communication between these wells. Right. And another conclusion from this well interference study is that actually between any wells here the impact is way too high to switch some of them into injection. So it means that the strategy of Waterflood is actually right here. So we need to put the injectors as far as we can, probably out there below the aquifer, below the free water level. But still, it is not a good idea to convert something here, because we will have a fast and major water breakthrough into offset producers. All right, so Now to the most interesting part. So, as I told you before, we found several wells with a quite close connection between them. So it means that if I change the rate on a well, the liquid rate in the area will redistribute quite fast, and I will get the liquid production increase in another offset well. So it means that if I have, let's say, two such wells, and one well has a water cut of, I don't know, 5%, and the other one has, well, like in this case, around 60%, then if I reduce the production in this well, and I reduce the water production, and I will increase the same amount of liquid production in about a month on another producing well which has well, almost zero water cuts, then I will get an oil production increase. And this I might do by simply switching the targets of my wells. So I need to restrict the rate of one well, then wait for months for the reservoir pressure to raise, and then increase the pressure drop in the good producer. So this is quite simple, quite fast, quite straightforward, and we can see it with these cross-well interference result we get from MRT. The next step is to forecast what, to quantify this effect. So what we're trying to do here is forecast it in three scenarios, like NFA, increasing the rate of the injector, and then reducing the production of watered out well and increasing the injector rate. So these are the three scenarios on the formation pressure plots. You can see the drop here, a moderate raise here, and a quite fast raise here, which in terms of additional oil production would get us several hundred barrels of oil per day. So now, as you all know, with this OPEC plus in progress, many companies need to reduce the production of their wells. And I think that the main target of all our subsurface teams now, when we're facing this problem, is to reduce it wisely, so we would perfectly fit the oil production limit and minimize the lifting costs. So we would inject minimum water to get this oil, and we would produce minimum water again to get this oil. Right. So in this particular case, I'm just clearly demonstrating how it can be done, and based on what information. All right. Before we jump to other cases, I need to introduce you to another technology. The last introduction slides, guys. I'm sorry. So this technology is called PCT, pulse code testing. So it is our own, well, proprietary kind of the interference testing. So as you recall, the previous technology, MRT, bases upon the rate and pressure measurements which also already exist. So it means that you already have a long enough story of your pressure and rate measurements, and you can understand the cross-well interference with this data only, without needing to interfere into production or go into some field studies and so on and so on. But in many times it's not the case. So sometimes we need to still organize a field test in order to understand what's going on between the wells. Sometimes you just don't have a PDG, or the PDG data is lost. Well, there are different cases, right? So the idea of the technology is to create a pressure disturbance in one well, which we call a generating well, and it would be a periodical pressure disturbance. So in the simplest case, for example, the generating well is the injector. It might be producer anyway. So if it is an injector, we would inject and then shut, then again inject and then again shut, and so on and so on. And then we will create a pressure disturbance around this well, so the pressure will go up and down, and then this disturbance would propagate through the reservoir, and it would lose the amplitude, and it would shift a bit in time, and then it would reach the offset wells, which could also be producers or injectors. And once this response reaches the offset wells, we record it with the pressure gauge, and then we see by the amplitude of this response, we see the transmissibility, average transmissibility of the reservoir between these two wells. And with this, I would say, phase shift, time shift of this well, so-called wave, we can see the pressure diffusivity. So it is like the speed of pressure propagation. Okay. So given these two numbers, the transmissibility and pressure diffusivity, we may understand a lot about our reservoir and about how our wells are connected and what's happening between them. Right, so let me show you just a couple of cases of this technology. Right, so case number one. Again, this is the SP paper for this case, if you want to see more info on that. So, estimating the vertical displacement efficiency with PCT. So, some of you probably do remember this picture because I have shown a part of this case a couple of months ago in my first webinar. But now we're focusing on, well, another deliverable of this study. So, we have this injector in the middle and several offset producers. So unfortunately we don't have any PDG or ESPs here. All these wells are on a natural gas lift, and we don't see any injection impact at the moment, though we started it not so long ago. But still, we would very much like to understand what's going on with the injection. So we organized this pulse code testing here. We put down run down a gauge in this well and several gauges in these offset wells, and then we pulse with this well. As I told you before, just inject and then shut in, inject, shut in, inject, shut in, and then by the response in these producers, we estimate the transmissibility and pressure diffusivity. So the raw pictures of the test you can see in the paper. I will just show you the results. So these are the raw results, the transmissibility and the pressure diffusivity. You can see there is some difference between the numbers here, and you probably remember the diffusivity was converted into dynamic permeability. Remember by my last webinar. So we found that the dynamic permeability of this field is, well, like 1 order of magnitude higher than was expected from the static model of our client. And we adjusted the model, adjusted the porosity permeability correlation, and gave, well, a more clear view on the reservoir properties around these wells, at least. And the second result, which I'm showing you now, is that through this transmissibility, we understood the connected thickness. So, this is a carbonate reservoir, by the way. The pay is quite thick. It's more than 100 meters. And you can see in these red boxes the values of connected thickness estimated with the pulse code testing. So this is actually a very bad news. So you can see that according to the cross-well pressure impact, we only have a small ratio of pay included in the displacement process. So you see here it's like less than 10%. Here it's, well, nearly 1/3, right? So if we put these results on a cross-section, And we also plot the production logging data over this cross-section. One might get an idea on how, geometrically, this connected thickness is situated in this cross-section. So together with our client, we reviewed these results, and we believe that the most probable option of where the displacement is going on is here. So according to the production logging and our estimates from PCT, we now have a pretty certain understanding that out of these three pays, I think you can see the upper pay, the middle pay, and the lower pay divided by these shale breaks. Only the middle one is actually included in the displacement process. Only here we have oil displaced by water, unfortunately. So it means that we need to selectively stimulate the upper and lower pay, and then try to build another pressure maintenance system based on more productive injectors and producers, and trying to align the displacement process between these two layers. Another thing we saw here is that there is a correlation between the distance between wells and the vertical displacement efficiency. It means that the larger the distance between the wells, the less communicated they are. So it strongly points to the necessity of additional drilling to tighten the well spacing on this field. And this is an idea which we share with the subsurface team of our client. And now we're trying to prove this idea to the management of this oil company. All right. And now let's go to, probably the last case for today. Estimating thief injection ratio with pulse code testing. This is one of the recent cases. Also carbonate reservoir, by the way. We have a small deposit right here. We have several producers well and only one injector. So we want to understand if there is any impact from this injection to these producing areas. So by the way, this injector is, I think it's injecting more water than all these producers produce liquids. So it means that the displacement ratio is more than 1. But still the reservoir pressure is dropping, right? So there is an obvious problem, and we want to understand the nature of the problem. So we run a pulse code testing. We use this injector as a generator and these two producing wells as receivers. So one of them was shut, I think the most distant one, right? And this one continued working. So the beauty of the PCT is that using the modern pressure gauges, modern mathematical tools, modern software solutions, we are getting rid of the restriction that most of pressure interference techniques are having, which is we need to shut receiving wells. So in many cases we do not need to shut receiving wells, and it opens a lot of possibilities to use the pressure interference testing in field analysis, right? So here you can see the rate of these receiving wells. Here 0, and here, you can see it's still produced during the test. And we have the the blue is the pressure itself, the red is the detrended pressure, and this black dotted line is the pressure response we found in this test. So you can also see how we created the pressure disturbance. So we inject here, and this is the pressure in the injector itself. So we inject here and then shut in, inject and then shut in. Here you can see that we had two target rates on this injector, like the high rate and the low rate. Okay, now let's go to the results. So once we estimated the diffusivity and transmissibility here, we compared it to what was expected from the open hole logs, and we saw that the pressure diffusivity is well, actually corresponding with the values we were expected to see. So it seems like the permeability is fine. There is, of course, a connection between these wells, and the permeability looks like open hole log prediction. But the magnitude of the response, which is based on the transmissibility, right, is very, very low. So it means that somehow we lose most of pressure impact somewhere along the way. And the most probable scenario here is that this injector is losing most of the water into the thief layer. Now let's see what we see with this pressure data on the injector itself. I hope you can read these plots, guys. This one could be quite complicated. So this is a series of log-log plots for one single test, although it looks like three different wells. So plot number one is what we see with the shut-in. So the transmissibility is somewhere right here. We can see a long linear flow, so we can see the fracture here, right? And we see a very, very low transmissibility. When we start injecting, we have a completely different picture. So this is an injection. Yeah, I'm sorry. I think I missed this. Well, okay. Anyway, so this this plot here is the log-log for the low rate, in fact. So still the transmissibility is, well, dramatically higher than what we see on the shut-in plot, right? And another thing here is the high rate. So what we see with the high rate, when we start injecting with the high rate, we have a pressure response which shows us the even higher transmissibility, right? So this type of plot only points to one thing. We have an induced fracture in this well. So when we start producing, start injecting, we have the dynamic fracture, which connects our perforation with a thief layer. And once we shut the injection, this connection closes as the fracture is dynamic, and we don't have any problem there. And we see the response from the target pay only, which is in fact very low permeable, and this transmissibility, well, I would say corresponds with the response we were expected to see. Okay. So I think that one of the interesting parts of this case is the subsequent production logging. So after we performed this PCT, our client called for production logging company to try to understand what is really going on in this well. And what do we see here? So we have a temperature panel here, a noise panel here, and you can, as a matter of fact, you can see that well, with the noise panel, I think you can see right away that we have this cross flow downwards. So this is the perforated pay, and on a small rate, low rate, we have a lot of noise here, and on a maximum rate we also have a lot of noise here, which means that a lot of water is moving downwards somewhere near the well, probably behind the cement, or along the frac, and we are losing a lot of water into the underlying pay. And you can see that the temperature is actually doesn't react to this as sharp as we would expect to, because the problem with the temperature logging, which is by the way my favorite logging method, but when you have water moving through the fracture, then the temperature response is not as sharp as you would expect it to be in the porous media. So it means that sometimes you can't even estimate the magnitude of your injection loss into the thick layer with the temperature logging. But here we can perfectly do it with the noise power. And our colleagues from the production logging company estimating the target injection in 10%, which corresponds pretty close with what we said in our PCT report. We said, I believe, from 5 to 7%. So, well, given the accuracy of both methods, I think this is a very nice match. So now we can see the real picture of what's going on this deposit. So unfortunately, out of this enormous amount of water we inject in this injector, only a very small part is going into the target layer, so it causes the reservoir pressure drop. And if we would be able to create, well, several points of injection, maybe converting some wells or drilling dedicated injectors, then we would probably be able to raise the pressure and support the oil production on this deposit, as on many other deposits with the very same problem for this client, right? Okay, now as I'm about to end the slides, I just want to ask you another question. So speaking of this thief injection and this induced fracturing problem, I would very much like you to type in the chat if you have the similar problems on your fields, because we have another technology which is quite innovative, quite new, which I would love to share with you if it would be interesting for you. So we have another technology of analyzing the injection data in order to understand the amount of the thief injector by well testing. Okay, so again, if you're interested, please type it in the chat, and we will probably run another webinar dedicated on this problem. Right, so now I want to thank you very much for joining. I want to thank the NAFTA College for creating this virtual venue, which I admire, and this is a perfect way of communicating with our colleagues through this, well, troubled time. Okay. Also, I would like to thank all my colleagues who helped me to prepare these slides. And I would like to announce that soon we will have another webinar, which will be run by my colleague Danila. I think it will be on two-dimensional modeling and what it can bring you, and how it can improve the understanding of your reservoir and your cross-well communications. So we will, of course, notify you all when the date is set. And now I will just open the chat, and we will see if you have any questions. All right. how many cells of MRT needed to be able to give suggestion to fine-tuning the water flood? Right. So, Guru, thank you for the question. So, as a matter of fact, it was a field-wide analysis. So, we took all the wells in the field. So, you only see one deposit. Yeah. By the way, I think we're talking about this slide, right? So you only see one deposit of the field, but in fact we had, I believe, about 60 MRT cells here, right? But actually, in most cases, we would just focus on the problem areas. So it is absolutely possible to give some recommendation for only for the problem areas of the field, and then the time of the analysis and of course the cost, right, would be much lower. Okay. The next question is what represent the number into boxes on the plot? Right. So this is one of the problems because I don't know now what. Right. I think we were talking about the same plot. Right. So the numbers inside the boxes is the formation pressure around these producing wells in bars, I believe. So we see about 200 bars here, 270 here, by the way, but this is actually caused by the water breakthrough from this well. And here we have lower pressure, 150, 160, and these are the areas of the most pressure drop. So we have the reservoir pressure lower than 100 bars. And the initial pressure, I think I have to say that the initial pressure here is about 280 bars. Okay. Okay. Right. Some more oil produced if unswept oil. That's right. That's right. What year? Of water flood? Yeah. So you see that the pay is quite thin here. So I think it's about 8 meters, and the well spacing is quite tight. Also, the permeability, well, I would say it's low, but considering many Russian fields, I think it's quite normal. It's about 20 or even 40 millidarcy. So it means that once we start to inject in this well, we had a response in, well, right about a month only. So it's a quite fast reaction, which we were able to see in no time. Do we need shut-in when using PCT? Well, I think I replied this question right in a way, but still we need to create a pressure disturbance in a generating well. This would be #1 priority. So it means that sometimes we need to create a big pressure disturbance, and the only way to do it is to shut, for example, the injection well. Shut and then inject, shut and then inject. But sometimes, again, judging by the fluid mobility, the distance, the PVT properties, sometimes we can just, decrease the injection rate and then increase it. Then again, decrease and again decrease it. So it would mean that we do not need to shut any well, nor the generating nor the receiving. Right. So in each case we need to pre-model the test. It means that we have like the expected formation properties, expected PVT, expected pressure impact, and then we pre-model the test in order to understand, well, at least the order of magnitude of our response. And if we may register this response with the downhole gauges we can afford in some well, right? Okay. Did you conduct any tracer survey? About the tracer. So the results of the pressure interference studies, and MRT and PCT are both pressure interference studies, are often compared with tracer studies, and I would say that this is not strictly correct, because the tracer is only telling you if you have any water in this well coming from that well, or if you have any communication between these wells at all. So it means that if you get the water in the producer from your injector, then yes, of course they are communicating. But the amount of this communication, and is it a good or bad communication, it's often unclear with the tracer result. So I'm trying to say that in many cases you would see that you don't get any tracer in a well, but still these wells are pretty closely connected, because there is another well between them, for example, and it could be a producer or an injector, and you won't get any tracer in an offset producer, but still when you shut this injector you will see a pressure drop on that producer. So it means that the pressure response does not work like a mirror of the tracer results. So I think these are technologies which complement each other, and we need to know what can be actually achieved with the different methods here. Okay. But answering to your questions, yes, we had some tracer studies which were run right before, right after our tests, and the main conclusions we had are confirmed with the tracer studies. Any specific reason? Right, why the generating well is located in the crustal location. It doesn't matter. As a matter of fact, it's just a coincidence here. As a matter of fact, we have a lot of interesting cases on both technologies, but some of them are quite recent and they are not published yet. And unfortunately, due to NDA, I cannot show you the pictures at the moment. But I think it will happen soon, and we will run another webinar. I will show you next time. I will show you several more interesting cases. Yeah, but yes, in these cases I'm showing you now, it's just a coincidence that the injectors for PCT are located in the crustal area. But as a matter of fact, it doesn't matter. It could be an injector somewhere outside your oil-water contact in the aquifer zone. Doesn't matter. It only depends on the distance and the mobility, and is a matter of a pre-design. All right.